All right, everyone. Hello, I'm Ryan, and let comments are bad equal to true. So recently I read about this little thing called the 5 whys, and all that is just a little technique where you just ask why over and over again 5 times to sort of just deduce the root cause of any sort of problem. And I was thinking that we could use that right here, right now, to figure out, well, I guess my title, to figure out why let comments are bad equal to true. You know, why comments bad? All right, let's try. So why comments bad? Well, maybe they're unnecessary, right? Maybe they don't really add to the code. Maybe they don't really contribute to what the code is trying to sort of express. And all right, well, why are they unnecessary then? Maybe they're trying to explain what should be readable. I mean, you know, code is, you know, fundamentally designed to be human readable. Code is, you know, you're supposed to be able to look, unless of course you're looking at assembly or anything like that. So, all right. So why are they trying to explain what is readable? And maybe the person who wrote up the code with the comments, maybe they just have poor coding standards. Maybe what they wrote is just so illegible that they can't actually justify having it unless they have some comments, you know? And that's it. We're 3 whys in, not even 5 whys in, and we've already kind of deduced the root cause of the problem here. Poor coding standards, or, you know, poor taste, if you will. I hope you will, because this talk was inspired by this guy, Linus Torvalds. So I'll read you out the quote. So the sign of people that I really want to work with is that they have good taste. And, you know, good taste is about really seeing the big patterns and kind of instinctively knowing what the right way to do things is. And, you know, this was a TED Talk, an interview about him, and the talk was about him. So he didn't really get time to really sort of delve in deep into the whole idea of taste. And that's kind of what I was hoping this talk would be. Sort of that exploration of, you know, what good taste is. And kind of be that sort of, you know, uni lecture that I never really got at uni. So yeah, and I'll share a link of that at the end, but for the talk. Anyway, so just quick thing about me. I do this stuff. If anyone, for some reason, knows any OpenGL, you know, you can talk to me and I'll talk back. It's pretty obscure. I don't know why I've got that up there. Anyway, so let's actually get onto the talk about these things. These are sort of techniques that kind of amend the most common things I see wrong when I'm looking at other people's code. And, you know, this talk is, I don't want you to kind of come away from this talk thinking about these just techniques, because I can show you a million techniques, right? I can show you all the techniques in the world, but obviously you should be keeping some, you know, techniques and tools in your tool belt. But I want you to really think about how these techniques sort of allow you to see a problem from a different angle and sort of see the clever ways that you can approach a different problem. Because while you can always go in and write code that just technically works, you really shouldn't do that. You really should just take a step back, plan out, and think about how you can make it more sustainable, you know, extensible, maintainable, all that stuff. So yeah, that's what we're talking about tonight, all right? And let's start with naming conventions, because I know that no one in this room is completely innocent when it comes to these. So m_s name. You really shouldn't have to do that. You shouldn't have to be embedding information into variable names, function names, whatever. Yeah, you shouldn't have to do that. Instead, what you should do is you should just be very, very super duper literal. I should be able to look at your code and look at the variable names, function names, method names, whatever, and just kind of derive meaning from that. And it should be then just self-explanatory and should be very expressive. And obviously stick to the naming convention, you know, snake case, camel case, whatever, pick one. But yeah, just be consistent. So let's take an example of something that's pretty bad. But why is it bad? Don't worry, I'm not going to do that 5 whys thing again. So let's just take a look through it. So, you know, extract. We're extracting something. What are we extracting? I don't know. We've got an await keyword. Maybe we're doing some sort of asynchronous, you know, database query, API call. We've got this distance. We've got 2 dates. I don't understand. I don't understand what's going on. Like, your guess is as good as mine. Well, here's the actual code for that. That's what's going on. And that asynchronous call right there, yeah, that was a bit of a trick. That doesn't actually do anything. Instead, and by the way, this this is real code. Oh, actually, I should probably explain what the function does. All it does is it gets the difference in months between two dates, and that's it. Yeah, and this is actual real code that I pulled from my code base at work. And I'm pretty sure I'm allowed to show this because the person who wrote this code just straight up copied it from Stack Overflow. So anyway, so yeah, we can do better than that. And this is better. This is much better. Look at that. So month difference equals helper.getMonthDifference. That's it. Literal. Very literal. Very just that. It's that simple. And you can see that I'm actually following the same sort of naming convention as the the JavaScript standard library for getting months and stuff like that. Oh yeah. Well, the difference is that it's just much more very literal, very expressive. It kind of explains the code, what it's doing. So. Oh yeah. Well, don't worry. I'll explain why there's a difference. But at the end of the talk, though. Anyway, so getting back to that. So that I'm just doing the same thing as a Java library. And actually, no, that's all I had to say about that. Let's you just do that, please. Anyway, let's talk about pure functions now. So it's pretty simple. Pure functions are just functions that don't change any sort of state outside of the arguments and the return value. That's it. So, and this kind of includes your database queries. It kind of includes like changing the states of variables within like member variables or global variables and all that sort of stuff. And most of your code should be this. Most of your code should be this. And so, and in this scenario that you do need to use, obviously you need to use database queries and change global variables. But in that case, you should push all that stuff to the top of the call stack. Sort of like where the chain of function calls sort of begins. And the reason why you want to do this is because they're just dead easy to unit test. And you'll see why that's really important later. But let's take a look at an example right now. So this is an impure function. And you can probably be forgiven for thinking that that looks like a pretty good function. But it's not, because it's an impure function because of this. So that's the database query. It's just some query getting some users. And right down here, we're filtering out the users based off of age. And that's just one line of code right there, the filter. But that could be maybe your entire like hundreds of lines of code of just business logic, right? And we don't want that to be coupled with the database query. So we can do better than this. That's how. It's not even that much. We just extracted our business logic out into a pure function. And you can see the users array there. We're filtering it out and making a copy, and a copy is very important. And and that's just a pure function. And up here, this is sort of like the top level of the call stack where the database query kind of lives. And now that function, the filters use convert, that's now really easy to unit test. And as you can see right here, this is Jest, or just think of your favorite, testing framework. But right here, we're calling the function itself, and then we're just throwing in a canned value into the function as an argument or parameter. I can't remember which one is which. And then we're getting just a return value, and we're just comparing it. And that's it. That's all you have to do. There's no sort of like database mocking. There's no sort of database anything. We're just testing a function, and that's it. And that's the power of these. And now, that's pretty good. So time for a bit of a tangent into unit testability. So this talk isn't about whether or not you should unit test, even though you probably should. But it's just because clean code is inherently unit testable, because it forces you to modularize out your code into separate units of code. So keeping that in mind, we're now going to talk about this guy, the dependency inversion principle, one of my little favorite techniques of making your code more unit testable. So this kind of stems from the idea that we don't want to ever couple our code to external dependencies, and we want to be able to write our code in such a way that we don't have to change it if we want to change an external dependency, or if the external dependency changes. And we can do that using just a common interface that gets implemented by the external dependency. And then our code can then reference that interface. And here's a little, here's a little analogy. So imagine your code is just like a jigsaw puzzle against another external dependency. That right there represents all of the places that you have to change your code because you didn't do the dependency inversion principle. That is a lot of places. If you want to change out your external dependency, you have to change in a million different places. You don't want to do that. That's bad. And this is kind of an example of that. So if I'm being perfectly honest, this is a pretty dumb example, but like, as you can see right here, we have my new startup called Tweeter, and we've got MongoDB and our SQL, and we're just kind of like conditionally checking the different, dependencies on where to use it. And this is obviously pretty terrible. A better example though would be probably like if you had multiple payment processes like your Afterpays and your PayPal, Stripe, and all that, and you wanted to support all of that. You don't want to be doing something like this because that could, like, this is just one example, right? This is one example, but like imagine in a real code base, you would have to change that in so many places. We can do, once again, better than that. So this right here represents the interface that gets implemented by the external dependency. And your code only ever references that interface. And by the way, when I say interface, I really do mean just your standard object-oriented interface. I do mean that you would just sort of find in your Javas and your C++, your TypeScripts and all that sort of stuff. That's what I mean when I say interface. And when you structure your code like this, your code is then modular against many different external dependencies if you sort of make a provider that implements that interface. So you can see right here, we can just easily swap them out. And the best example of this I kind of find is like just think about the standard USB Type-C, right? You can see that the USB Type-C, I don't really have to, well, the USB Type-C connection doesn't really have to care whether or not it's plugging into a MacBook or Lenovo. As long as the MacBook or Lenovo kind of just implements the USB Type-C standard, it doesn't really have to care. And it can be like a charger, a USB stick, or whatever. But yeah, it doesn't really have to care. So let's try that. Let's implement an interface without external dependencies. So you can see right there, these are the just two providers that implement the get users method. And that's it. The implementation details are just kind of contained within these providers. And then from our code, all we have to do is keep a reference to it, to the provider that we kind of implemented just before. And then we know that there's going to be a get users method right there. And so if we want to change our external dependencies, we can do that just by instantiating a new instance of that implementation of the interface. That's it. And then you can see right here, that makes it really dead easy. Whoops, there we go. Dead easy to just mock out sort of implementation of that interface, where we can just throw canned values out of the implementation. That's really good. That's bringing back to like that unit testability, really making your code more clean. And so yeah, that's it. That's the dependency inversion principle. But don't worry, I actually have one more tip for you. This tip, like, it is like the best technique for getting people who are new to your code base to actually understand your code. And that is to actually comment your code. Because, well, yeah, no, I know I just spent a bunch of time telling you why you shouldn't do that. And that's why, like, everything in the world, there's some nuance to it. And so that's why this comes with a little asterisk. Because, well, actually, you know what? Let's just lead with an example this time. That is the fast inverse square root. It's a pretty famous algorithm. All it does is just it calculates the inverse square root, but really fast. Yeah, you can see, like, and it's just like a really famous algorithm that has really famously bad comments. Like this right here does not say duck in the original source code. But anyway, so you can see right by looking at here, here, and here, yeah, you can't really derive much meaning from that. And even if this really, in like 2005, when id Software created Quake 3 and they actually somehow saw into the future and saw my talk and actually, implemented those naming conventions that I mentioned earlier, there's only so much information that you can actually cram into just a name, right? There's only so much you can do there. So in that case, it's pretty reasonable to do this, write a comment. That just tells me what the function does. So I don't have to go into the function and actually look at the source code and understand what the hell the person is trying to do. I can just use it. And that is like the case where comments are good. That, just tell me what the function does, tell me the arguments and their types, and just tell me what it returns, and that's it. And then you have like your one-off oddities, like maybe you're using some weird mathematical formula, or you had some weird hack that you kind of had to implement and you couldn't do it any other way. Yeah, that's where comments are good. Now, where comments are bad is if you're explaining how your code works, rework it to be more readable. Yeah, that's it. Thanks. I think I might have time for questions, right?
Yeah, you can just a few more. Anyone have any questions?
I remember there's. Oh, you got one. Okay.
Do you have any pro tips for detecting when comments are stale?
Don't write comments.
Correct. Love it.
What's up?
Just a quick one.
Hmm?
I reckon I get lost in my own coding if I can't remember what I was trying. Maybe I'm a bad coder. But when you retrieve from the database, any reason why you retrieve all values and then filter it? Like,
Oh, that's just an example.
Just a bad example. Database gone.
Oh, it's a really bad example. Yeah.
Shouldn't you push that down to the database?
Yes.
Retrieve back a smaller database.
Oh yeah, no, that's absolutely what you should
If that
do.
was like 600,000 users,
You shouldn't be doing that.
You just blow up your memory.
Oh yeah, no, that's a very good point. Anything else?
Yeah.
Yep.
Probably what I'm going to say, not everyone will like it, but anyway.
Mm-hmm.
So you are trying to get expressions of functions, of pure functions, bringing one code into that. See? The problem is that this creates your program, make it too big. If you take a program written for someone else and want to understand what he's doing, I have to throw all the time forward, backward, because of the small pieces. I don't have the full picture.
Oh,
See,
so
that's the problem. You solve the problem for square root code. For square root is the last frame, right?
yeah, this.
Imagine each operator in a several function. How could read it? It would be impossible to read this code. Thank God that it's not yours. This code would be impossible to read because you have seven commands here, and you're advocating put everything into a separate function, right? That's why I understand you. If this code was organized as that, you would be unable to read it at all.
Well,
Here,
okay.
the comments are bad, by the way. It's either floating point. I thought it doesn't give me any clue for that. But I was expecting would be much more explanatory to see how this would work. But talking about splitting into small functions, sometimes it's not a good idea. It has to be a compromise. What is written with what is not written.
Well, there is
Too much about that.
That is. No, don't worry. So there's two things kind of in that sort of statement. Is that there's the fact that you can't really make something so specific that you'll end up with a massively tall call stack. But what you kind of would do in that case is you would make your top level of the call stack just a bit bigger, and then you want to make as every single function that's a bit smaller, exponentially more generic, right? So you can use them in many different places. In this case, that is pretty generic. So it kind of makes sense that this is just like a small function that is at the bottom of the call stack. At my work.
There don't need any clue with this comment. This code doesn't give any clue, to be honest. I know how the code works. I remember, but without that, I would be unable to understand it at all. This program.
So you're kind of blending two questions together there. One of them's about pure functions, and one of them's about comments.
Anyway.
Anyways, maybe we move to the next track now.
Okay.
Another round of applause for Ryan. Thank you.